Hello everyone, welcome back to Energy Conversion System 1. In this video, we will talk about the solutions for the homework on centrifugal pump. The first question is about an impeller of a centrifugal pump rotates at a speed of 1200 RPM and the radius of the inner and the outer part of the impeller is 480 and 960 millimeter respectively. And another clue is that we have no whirl at the inlet. And then we need to determine the total head developed by the impeller if the flow velocity leaving the impeller is 7.2 meter per second and the blade angle at the outlet is 45 degrees. Now from these informations we know that the blade angle at the outlet has an effect to the geometry of the centrifugal pump itself. Now that we know that the beta 2 is 45 degrees and therefore the centrifugal pump that we are working on is the backward facing fans, and then to get the head or the Euler head of this pump we can use these particular equations. But according to the information that we have, we are still missing the U2 or the tangential velocity at the outlet of the impeller. So therefore, we will need to use these equations to get the tangential velocity. And that is U2 is equal to P multiply with diameter 2, multiply with the speed or RPM and divide it by 60. According to the calculations, we can get the tangential velocity at the outlet is equal to 120.63 meter per second. And now we can move on and get into the Euler head developed by the impeller. So from this point, we know that according to these equations, the Euler head is a function of the tangential velocity at the outlet multiplied with the tangential velocity at the outlet minus to the radial velocity at the outlet multiplied to the cotangent of the blade angle of beta 2 at the outlet and divided by gravity. Now we can put the number that we know that the tangential velocity at the outlet or U2 is equal to 120.63 meter per second multiplied by the 120.63 meter per second minus to that of 7.2 meter per second. That is the value of our radial velocity at the outlet multiplied by the cotangent of 45. And then divide it with the gravity accelerations of 9.81 meter per second to the power of 2. And now from these calculations, we can find that the Euler head is equal to 1394.80 meter. Another way to solve this problem is by looking back at the basic equations of the Euler head itself, that is equal to U2 multiplied with Cx2 minus U1 multiplied to that Cx1 divided by gravity. Now that we know from the question is that we have a no whirl conditions at the inlet. That means we have no Cx1 at the inlet, or Cx1 is equal to 0 at the inlet. So we can cancel this and our equations becomes U2 multiplied with Cx2 divided by gravity. Now we need to get our Cx2 from this velocity triangle. If we look at this, this is Cx2, that is can easily be Cx2 is equal to U2 minus Wx2, where Wx2, or the relative velocity at the outlet, is equal to radial velocity of the radial component of the absolute velocity at the outlet divided by tangent of beta 2, or blade angle. We know that it is 7.2 meter per second, and we have a blade angle of 45, that the tangent itself becomes, this is equal to 1, so that our Wx2 is equal to 7.2 meter per second. Now that we get our Wx2, we can go back to our Euler equations here, and this becomes Euler equal to U2 minus U multiplied to U2 minus Wx2 divided by gravity. Now we get the number Euler hat equal to U2, that is 120.63 multiplied to 120.63 minus 7.2 divided by the gravity accelerations of 9.81, and it will give us the same answer as before, that is around 1394 meter per second. So we can solve this problem by using the blade angle UVAC, or going back to the root of the actual Euler hat equations. Both will give us the similar solutions. The second question is about the centrifugal pump that has a discharge of fluid equal to 4 cubic meter per minute, and the pump diameter is 1.5 meter, and it has a tip speed, or U2, of 12 meter per second, and the blade itself has an angle of 45 degrees at the outlet, and the fluid velocity, or C radial 2, equal to 1.6 meter per second. We have no reel at the inlet. That means that Cx1 is equal to 0, and then we have slip factor, or tau s, equal to 0.8. Now that we need to find the Euler hat and the torque of the pump. Now, same as the previous problem, when we want to get the Euler hat, we can approach this problem to find its solutions based on the effect of the blade outlet, or we go back to the actual equations of the Euler hat itself. Now we try to find the Euler hat based on the actual equations, or the basic equations. We know that we have no reel at the inlet, therefore we can cancel this, that Cx1 is equal to 0. Then we only have U2 multiplied with Cx2 divided by gravity. And we know that to get Cx2, we can look at the velocity triangle, that Cx2 is equal U2 minus Wx2, and we can get Wx2 from the triangle. And then Wx2 is equal to Cr2 divided by tangent of beta 2. So we can put that our Cr2 is 1.6 meter per second, and then tangent of 45 is equal to 1. 45 degrees is equal to 1. Then our Wx2 is 1.6 meter per second. And then from this, we can go back to our Euler equations and put that U2 is equal to 12 meter per second, multiply with 12 meter per second minus to 1.6 meter per second, and then divide it by 9.81 meter per second to the power of 2. This will give us the answer of Euler hat of 12.72 meter. And this is the conditions where we have no slip. When we want to consider the slip, our Euler hat becomes with slips multiply with the slip factor, it becomes 12.72 meter multiply with 0.8, this is our slip factor, and the hat with slip is equal to 10.18 meter. Now on to the second part of the questions. We are being asked to find the torque of the pump. As we know, the basic equations of the torque is pump power divided by the angular velocity or the tip speed velocity. As we know, that is equal to 12 meter per second. That is our angular velocity. And from this, we need to find the power. Power itself is equal to density or rho multiply with gravity multiply with flow rate or key and multiply with the head. Now let's assume that we are using the slip conditions to get our torque, and then this is U2. So torque is equal to density of water is 1000 kilogram per cubic meter multiply with 9.81 meter per second to the power of 2. Our Q was around 0.067 cubic meter per second, and the head itself is 10.18 meter, and then we divide this all with 12 meter per second, and then we get the torque around 418 Newton meter. So it's quite straightforward to solve these torque equations, but don't get confused by the naming of this angular velocity. Sometimes they call it angular velocity or tip speed velocity. So basically these are, or this is the different naming of the same physical number. The last questions of the homework, or the third questions, we have the informations of a centrifugal pump that develop a head of 27 meter and it runs at 900 RPM. Therefore, the flow velocity at the outlet is 3 meter per second and the blade angle is 45 degrees. We need to find the diameter of the impeller. Now we can solve this directly from the basic Euler hat equations that we've been using over the last two questions, that U2 CX2 minus U1 CX1 divided by gravity. Assuming still we have no reel at the inlet, we can cancel this, and then we can run through the questions and these equations. We need to derive a bit that U2 CX2 divided by gravity is equal, that we know that U is a function of P, diameter, and N divided by 60 if we have N at RPM. If it's already RPS, we don't need to divide it by 60. So we put it like this. U2 per gravity multiplied with U2 minus WX2. And another step is P E2N divided by 60 divided by 9.81. This is for this one. And we go again for P diameter 2 and divided by 60 minus, and we know that WX2 is equal to CR2 divided by tangent of beta 2, and our CR2 is 3. This is divided by tangent of 45 or equal to 1. And from here we put the number on it. P diameter 2, this is things that we need to find, n equal to 900 divided by 60 divided by 9.81. This is in one bracket. This is another P D2, the one that we're looking for. 900 divided by 60 minus 3. And by doing so, we know that our Euler hat is equal to 27. That the diameter at the outlet is equal to 0.38 meter. So it is quite straightforward to solve this problem. So we can go back to the basic Euler hat equations basically to get the diameter. As long as we know the substitutes of each velocity components, we will get the diameter at the end.